So you remember that the state of a simple compressible system is completely determined once two properties of that system are set. Say you set the pressure and the temperature. Well, if I have a container of steam and I set the temperature and property at some value, then the density is set, right? I can't change the density independent of the pressure and temperature. Another way of saying that is that the specific volume then is set. Similarly, the amount of energy per mass, the entropy, the enthalpy, all these things, all these properties of the steam are set once I have set two properties. And so it turns out you can actually make property tables, and it makes it very easy to relate pressure, volume, and temperature as well as all the other properties. In fact, pressure and temperature are the two we usually measure. They're easy to measure. You've got a pressure gauge, you've got a thermometer, and from that we can look up all the other properties that we want. So if you imagine steam in a container and you put it at various combinations of pressure and temperature and you figure out ways to measure all of its properties, obviously density or specific volume is one of the easier ones to measure, but the others you can figure out as well. And then you can tabulate it. Now I've shown you the saturated tables in the back of your book, but I haven't shown you the superheated table. So go back to table A4 and turn the page a few all the way over to A6. And I don't care if you go to A6 or A6E, you probably need to mark these as well. These are called steam tables. And they're called steam tables because they represent the pressure, volume, temperature, and other property relationships of steam. So if you say look up a temperature of, I'll read what I've got here, 240 degrees Fahrenheit, a pressure of 1 psia. Well, at that combination, which is the upper left section of this chart, or this table, you can read off the specific volume. I can read off the specific volume as 416.4 cubic feet per pound of steam. I can read off the internal energy. That's what? 1091.2 BTUs per pound, where BTUs are an English unit of energy. Now, notice that when you read these off, let me give you a really quick practical hint here. When you read out of a table like this, just grab a piece of paper or a ruler or some kind of straight edge and lay it down on the page so that you can go across to the correct number. I almost read off 1077.5 BTUs per pound mass, but I was trying to read it off at 240 degrees Fahrenheit. That value of 1077 is at 200 degrees Fahrenheit. It's very easy to go across and go up or down to the wrong row, and you lose points on exams, you don't understand homework, it causes all kinds of problems. So do yourself a favor and just grab a straight edge and read across with that. Okay? So the easiest way to relate pressure, volume, temperature, and all the other properties is just to read it out of a table. Now, it's even easier when we have a mixture, right? When we have a vapor-liquid mixture, because in that case, only one property is required in order to set all the other properties, of course, assuming that we're at equilibrium. So the saturated tables that I've pointed out to you already only require one property, and then you can just go straight across on that line and read everything else off. So if there are two phases present, liquid and water, we have to go to saturated tables, whereas if there's only one phase of gas present, then we can go to the superheated water table, also known as the steam tables. This is about the easiest way to read things off. And these, actually, it turns out that these are based on more complicated equations of state. Okay, but you'll learn about that more in the next thermo course. For right now, the easiest equation of state that you're probably familiar with is the ideal gas law. The ideal gas law, if you think about it, is simply a relationship between pressure, volume, and temperature. And it says that PV equals mRT. Now, you may have learned it as PV equals nRT in chemistry, where N is the number of moles and R is the universal gas constant. But so much of the time in engineering we're interested in the mass of a system and we want to use it, that we'll use gas constants that vary and are not the universal gas constant. So we'll have a different gas constant for air, a different gas constant for carbon dioxide, and it's just a convenience thing. So what you should do is go to the first page of both appendices, the English and the metric appendices. You should put a tab there as well, because the first page of those appendices has some very valuable information, not the least of which is the gas constant. Now notice, I want you to go to the first page of the metric appendices, so that's the first appendix. Okay? You may have to pause the video as you go to get there as I'm talking, but when you go there, you should note that there's a gas constant R, and it has units of Well, I got to think for a second. It's energy, so kilojoules per kilogram per Kelvin. Okay, same units as heat capacity, but we'll get to heat capacity later. All right. Now, here's something you need to know. A kilojoule is the same thing as a kilopascal times a cubic meter. Now, I know I'm having you flip around in the book a lot, but throw a tab in the page where we are on the first page of the metric appendices. Now go, and I can't remember, I always forget because in the 320 book it's opposite from the 220 book, but it's either the inside front cover or back that has conversion factors. I think it's the front in the 220 book. Wherever it is, go there and you will find under the energy section a conversion factor for going between kilojoules and kilopascals times cubic meter. They're the same thing. It's a one-to-one relationship. You need to grab a highlighter and highlight that one because we're going to use it over and over and over again. Okay? Just a practical note. Another practical note about the gas constant. Go to the English appendices, first page. Put a tab there while you're there. And notice there are two columns of gas constants. Okay? There's one with the units of BTUs per pound per Rankine. The other one has units of PSIA cubic feet per pound mass per Rankine. I want you to make a note. Put a note to the column that has the units of PSIA cubic feet per pound mass per Rankine. That's the gas constant R that you want to use in the ideal gas law. So just put an arrow to that column and say use in gas law. Put some stars around it or something so you don't forget it. Okay, because if you try to use the other one, it's correct, but you have to convert units, and it's less convenient. Okay. All right. So, in our use of the ideal gas law, we're going to use the form of the equation PV equals MRT, and actually, we might not even use that form sometimes. What we'll do is we'll divide both sides of the equation by the mass in the system, whatever that happens to be, however much it is. So we're going to put the mass with the volume. So you notice the next equation is P lowercase v equals RT. We'll use it in this form quite a lot as well. So that's just the total volume divided by total mass. It's the inverse of density. Now you might say, well, what could we do with this? Well, we could calculate the amount of mass of air in a room. And I've got an example problem later on where I do that. So you may want to pause this video now and go watch that one because maybe I've piqued your interest. Now let me warn you a little bit. Often students try to use the ideal gas law for liquids. In fact, on the first exam, students will try to get properties for a liquid and they'll say, well, where do I get it from? Well, the only thing I know is PV equals MRT. So they use it. Well, that doesn't work. It's the ideal gas law, not the ideal liquid law. There is no ideal liquid law that I know of. Okay? And certainly it's not this relationship. So don't try to use the ideal gas law on a liquid. It won't work, no matter how often you try it. Okay? Now I know on the first exam from experience that most students, not most, 25 to 50% of the class is going to try to use the ideal gas law on a liquid, and it won't work. Okay? So you might make yourself a note of this. I don't usually ask you to take notes. For me, it didn't work to take notes in college. For you, it may. So whatever works for you is fine. But even if you don't take notes, grab a pencil and write down the ideal gas law is not the ideal liquid law. Do not use on liquids. Maybe that'll jog your memory and you can get a higher score on the first test. Now, does the ideal gas law really work? Is it correct? Well, let's try to use it on something where you might think, it probably won't work. Let's use it on water. After all, water is a polar molecule, and the molecules attract each other a little more because they're polar. So they have some imbalance of charge across the shape of the molecule. So does PV actually equal RT? Well, actually, we have steam tables, right? And what do steam tables do for us? Well, they tell us the relationships between pressure, volume, and temperature. So you could actually use the ideal gas law to, say, predict volume for a pressure and temperature, and then go to the steam tables, look up that pressure and temperature, and see if the volume from the ideal gas law matches the volume in the tables, which is more like a measured value. If you do that, and then you calculate the percent error, so the actual value, that would be from the back of the book, the tables, minus computed, that would be the specific volume predicted by the ideal gas law at a particular pressure and temperature, divided by the actual, again, from the back of the book, and taking the absolute value, that is how you would calculate percent error. And then if we plot the percent error at various points that are combinations of pressure and temperature, you can see that the shaded area on the right has relatively low error. The ideal gas law actually does a really good job of predicting the behavior of steam as long as the temperature is relatively high and the specific volume is relatively high. In other words, as long as the density is relatively low. Now, if you think about this, we could do this for any point, really, right? Now, it doesn't make sense to do it for the area beneath the vapor dome, because in that area you've got a saturated mixture of liquid and vapor. And again, the ideal gas law, we would expect a lot of error there, right? Because we're dealing with liquids. So we really don't want to go much left of the critical point, and we certainly don't want to go down into the vapor dome. But we can get closer to the vapor dome, and as long as we're to the right of it, we're still dealing with something that is legitimately a gas, so we can calculate the percent error. How bad is the ideal gas law at predicting the PVT relationship of steam in this area? Well, what do you notice? Well, you notice as we move closer to the vapor dome and higher, you notice that the percent error goes up. I mean, I see going along the saturated vapor line, I see 6.0, 7.6 right on the line. So that's, you know, the error is creeping up. Now, it's not because it's a saturated vapor, because look, lower on the curve, we've got a 0.0, 0.1. The ideal gas law does a pretty good job of even predicting the behavior of saturated vapors at certain conditions. But as we move up on that slope, as a matter of fact, as we get closer to the critical point, which is the point at the top of the vapor dome, notice what happens to the percent error. It shoots up. It's ridiculous. Do you see that near the critical point? 271% error, 152.7% error. How would you like it if you went and you bought a candy bar and you paid with a $20 bill, or let's say a $100 bill, and the cashier gave you change that was 271% in error, right, and not to your favor? You would not be very happy at all. So the ideal gas law is not doing a good job, but notice where it's not doing a good job. It's not doing a good job around the critical point. That's where the ideal gas law really breaks down. That's one of the reasons that this is called the critical point. It's because that's where the gas misbehaves. It's kind of like a kid when you give them sugar, right? They got a lot of energy, they're going to run around and misbehave. Well, that's what gases do. In fact, every gas, not just steam, but every gas misbehaves or deviates from the ideal gas law prediction of behavior most around the critical point for that particular gas. Now, the critical point's not a critical point that's the same pressure and temperature for every gas out there. Each gas has its own critical point, but the behavior is similar for each, where the gas misbehaves worse around that critical point. So what if we define a correction factor? We'll call it Z. We'll call it a compressibility factor. And we'll define it as PV over RT. And you might look at this and say, well, isn't that ratio always 1 because it doesn't PV equal RT? Well, we've already found that no, that's not the case. And especially around the critical point, PV is not equal to RT. So this ratio Z could be 1 if the gas is behaving ideally, but if it's not behaving ideally, if it's a real gas, Z could be greater than 1, it could be less than 1, it could be equal to 1. Okay? So how do we know whether or not Z is 1? Well, generally, when the pressure is relatively low, real gases tend to behave more ideal. And what do we mean by low pressure? Well, we mean a pressure that's below the critical point pressure. That's how you decide if it's a low pressure. Okay? What about as the temperature goes up? Well, real gases behave more like ideal gases as their temperature goes up. Goes up relative to what? Relative to the critical temperature of that gas. So at temperatures high relative to the critical temperature of the gas, and at pressures low relative to the critical pressure of that particular gas, the gas will behave more ideally. Now, this is one of the most amazing things I think I've ever seen. I know it looks kind of boring to you, and let me warn you, this is just sort of a schematic. It's not the actual compressibility chart. It's just to teach you how this works. Look over in the legend at the various gases. Maybe you can read them, maybe you can't. They may be a little small in the video once I produce it. But I'll read it for you. We've got methane here, ethylene, we've got ethane, propane. If you know anything about chemistry, you know that these are organic chemicals. Methane, or methane as some people pronounce it, is just one carbon with 4 hydrogens around it. Ethylene, on the other hand, is 2 carbons that are double bonded to each other, and then you fill in with hydrogens around those, so 2 hydrogen atoms on each. Ethane is 2 carbon atoms with 3 hydrogens around them. Okay, fine. So we've got a bunch of organic chemicals here that are carbon and hydrogen. But if you look over on the other side, you'll notice that we also have nitrogen. Well, nitrogen behaves very differently. Nitrogen often behaves much like a noble gas, right? It's pretty much unreactive. It doesn't really interact with itself much. Doesn't have any polarity. That's similar to the organic chemicals. They don't have polarity. They're not polar molecules. But then we go down and we've included sort of an outlier on this list. There's water. Water is a polar molecule, and water often behaves very differently from organic compounds. And so this is where the saying comes from, right? Oil and water don't mix. Well, oil is an organic compound, and so the behavior of organic molecules is very different from the behavior of water. Carbon dioxide is another interesting addition to this list because it's carbon with oxygen rather than carbon with hydrogen, like typical organic molecules. And yet the data from all of these molecules follows the same trend. This is utterly amazing because how often do you have two very different things that behave the same way? Well, water is very different, and yet it's behaving the same way. And it doesn't really matter what gas you get, they all follow this chart. Now, that sounds really interesting, but what the heck is this chart? Well, remember I said that if a gas is at a relatively low pressure and relatively high temperature relative to its critical point, it behaves fairly ideally. This chart is a chart that plots the compressibility factor on the y-axis, Z, versus what's called the reduced temperature and reduced pressure. Well, what's that? Well, the reduced pressure and reduced temperature are just ways of measuring how close the gas is to its critical point. So you might say, well, what do you mean? Because I see a ratio over here on the left. It says reduced pressure equals pressure over critical pressure. What's that all about? Well, think about it this way. Let's say you want to buy a car and you've decided you want to pay cash for it. The car you want is $20,000 and you have $10,000 in the bank. How close are you to buying that car? Well, you got half the money, right? How did we figure that out? Well, we took the $10,000 over $20,000. So we're measuring how close you are to purchasing your car. If you have $19,999, you're pretty doggone close to buying that car, aren't you? And just plopping down the cash for it. Quick life hint for you. Dealerships make part of their money in financing your car in the interest. So don't tell them from the beginning that you plan to pay cash if you do, because they'll actually try to add in as many fees and things as they can to bump up the price of the car and make their profit off the sale of the car. Anyway, that doesn't matter. We're trying to measure how close the gas is to its critical point by taking a ratio of the pressure that the gas is at right now versus its critical pressure. That's called the reduced pressure. That ratio is a reduced pressure. And notice that it is dimensionless. Similarly, the reduced temperature is a measure of how close the gas is to its critical temperature. So put in the temperature the gas is at right now divided by whatever the critical temperature is of that gas. That gives you a ratio which measures how close the gas is to its critical temperature. Now, obviously, this number can vary between 0 and as high as you want it to go. But that's what we've done. We've plotted reduced pressure on the x-axis, and I think what confuses students is this is really a three-dimensional thing. It's really a three-dimensional surface. And the way we represent that surface is by making a family of curves for different values of reduced temperature. So if you kind of look at this, you can kind of begin to see it as a valley or a vein that comes down as we go down in reduced temperature from 2 all the way down to 1. So what you do to use the compressibility chart is you simply locate a single point. So let's say the gas is at 100 degrees Celsius. By the way, here's something really important. If it's at 100 degrees Celsius, you can't put it in to the reduced temperature calculation because it won't work. You have to convert it to absolute units. So make a note of this. The temperature you put into the reduced temperature and actually the pressure you put into the reduced pressure calculation have to be absolute units. They have to be absolute or total pressure and absolute temperature. Whether you're dealing in Rankine or Kelvin, that's what you need. You can't use Celsius or Fahrenheit. Now, another quick aside: the critical pressure and critical temperature are in the back of your book where we found the gas constants. So you might want to add a little bit to your tab there and write, hey, here's where the critical point properties are located, the critical pressure and temperature. Anyway, the way you use this is you use it to correct the behavior of the gas. So what you do is you say, okay, let's say you know the pressure is, I don't know, let's say 1 megapascal, okay? And you know that the temperature is 300 Kelvin. Well, you look up the critical point properties for whatever gas you're dealing with. You take the ratios of the pressure to critical pressure, temperature to critical temperature. That gives you your reduced pressure and reduced temperature, PR and TR. And then you locate one particular point on this graph, that pair of PR, TR. You locate that point, and you just go off to the left, and you read off the compressibility factor. So you read off Z, and what is Z? Well, Z is going to be something between about 1 and about 0, more like 0.2 or so. And so now you know the ratio of PV over RT. It's not 1, it's whatever you read off on the left-hand side. Now, another hint. If you listen, you're going to get more points on the test. Are you ready? Here's how students mess up. Students don't understand compressibility and they hesitate to use it. And so what they do is I give them some pressure and some temperature, and I ask them to calculate, say, the specific volume of the gas, and I warn them that it's not behaving ideally. So what students do is they use the ideal gas law with that pressure and temperature to calculate the ideal volume, and then they say, okay, now I've got PV and RT, I'll plug those in because Sisk has tried to help me through the problem. He's given me all these various steps, and one of the steps is I've got to calculate the compressibility factor. So now that I've got the volume from the ideal gas law, great, I'll just plug it back into PV over RT, I'll calculate Z, and away we go. And you know what number you'll find? You'll find 1, or very close to 1. You'll always calculate 0.99 something, okay? If you are on the test and you see Z equals 0.99 or 1.0, a red flag needs to go off immediately because you've done something wrong. You have not understood compressibility, and you must understand compressibility to solve at least one of the problems on the first exam. Okay, so I'm warning you now, if you get to that point and you see that you've calculated Z equals 0, you've fallen for the trap of trying to just apply the ideal gas law as if it's true, and it's not. Okay. What you have to do instead is use the pressure and temperature that I've given you, calculate the reduced temperature and pressure, go to the compressibility chart, locate the point that combination of PR from the x-axis and TR, the line, represents, and then go over to the left, read off the compressibility factor, and use that with the pressure and temperature that I give you, rearranging the equation on the y-axis to solve for the corrected specific volume. Now sometimes I'll be really mean to you and I won't give you a temperature, or maybe I won't give you a pressure, and so you can't calculate either the reduced pressure or maybe the reduced temperature. In that case you have to use something called the pseudo-reduced volume, and there's an equation for it there on the slide, and you use the actual specific volume, which has to be given. I can't just give you one pressure and expect you to use compressibility. I have to give you two properties, remember, because two properties are required to determine all the other properties of a simple compressible system. So I have to give you temperature and actual specific volume, or I've got to give you pressure and actual specific volume, or I have to give you pressure and temperature for you to use this compressibility chart. Okay, but if I give you specific volume, the actual specific volume, and I can give it to you in a tricky way by giving you the volume of the system and the mass in the system, expecting you to take the ratio of the total volume to mass. But if I do that, then you can calculate the pseudo-reduced volume. Now, it's not shown on this chart, but there are lines of constant pseudo-reduced volume as well on the actual chart we'll use in just a second. I'm going to show you the chart. But first of all, let's see some trends here in this schematic of the compressibility chart. One thing to note is that all of the data lines lie pretty much on the interpolated curves, right? So it doesn't matter if we're talking about water, which is the solid filled in circles. It doesn't matter if we're talking about methane, which is are the X's. The data lies pretty much on top of the lines. There's a couple of outliers. You see a filled in box for isopentane up there. Okay, but still, I mean, you could get a PhD off of this, okay? Or probably a couple if you discovered this. This is amazing fit of real data to interpolated lines. So, or I should not interpolated, but least squares lines, okay? This is really, really good fit of data, and it's amazing that such a wide range of gases behaves according to this and is predictable then, right? The deviation from ideal behavior is quite predictable. Okay. Now notice something here. Notice that For low pressures, what does it mean to be a low pressure? Well, a low pressure relative to the critical pressure. So that is where the reduced pressure is much less than 1. So on the x-axis, way on the left-hand side, all of the data points are grouped around about 1. So the compressibility factor is close to 1, and PV is equal to RT. That is the definition of ideal gas behavior. So sure enough, at low pressures, this chart says that gases behave quite ideally. What else? Well, notice that at relatively high temperatures, so we've got a curve here that is the reduced temperature greater than or equal to 2. What does that mean? Well, reduced temperature greater than or equal to 2 means that the actual temperature of the gas is about twice of its critical temperature, okay, or more. In that case, notice that this whole line is pretty doggone close to 1.0 for the compressibility factor. So that means that gases behave ideally when they're at temperatures about double their critical temperature, regardless of the pressure. What else? Well, notice the point where gases misbehave the most, or in other words, their compressibility factor is farthest from 1, occurs where we have a reduced pressure of 1.0. That vertical line there, that second division line from the x-axis, that vertical line, is 1.0, representing pressure equal critical pressure. And notice that the curve, that really dipping curve that we've got, is reduced temperature equal to 1.0. In other words, the temperature of the gas is exactly at the critical point temperature. At that point, where those two are true, that's where we get the worst compressibility factor, or the compressibility factor that is farthest from 1, and that's the least ideal point. Now, the chart I'm about to show you is really just from a reduced pressure of 1.0 back, because really that section, although it's only the first two divisions of this chart, really that's usually the most beneficial, most useful portion. So the actual chart looks something like this. So notice that the reduced pressure axis only goes up to 1.0. Now these are called Nelson-Obert generalized compressibility charts, or just compressibility charts. And notice that this is not the whole thing. This is just from a reduced pressure of 1.0 back to 0. Once we get to 320, we've got two different charts that are all of it together. Actually, we've got one that's the whole thing from 0 up to about 7 or 8, I think. And then we've got a zoomed in portion, which is this. Because again, this is the portion that's particularly useful most of the time for our purposes. Now notice that there's a nice little inset here. Now you should find this chart in your book. It's in the appendices, and it's actually near the end, or maybe even at the end of the metric appendices. If you need to, pause the video, go find that now and put a tab there. That's another place that you desperately need a tab in your book. Notice that the inset here has the equations for reduced pressure, PR equals P over P critical, so you don't have to memorize it. You might want to highlight it though. Reduced temperature, TR equals T over TCR, the temperature of the gas over the critical temperature of that gas. And then also for the pseudo-reduced volume. So highlight all three of those as well, because they're really useful. The area near a compressibility factor of 1 way on the left is really hard to read off. That first major division is hard to read off. So there's an inset of this in the chart as well. And it's just a zoomed in version of that region up there by compressibility factor equal 1. So that's good to know. You can read it off a little more accurately there. But what you'll notice is there are also lines of constant reduced temperature. So they slope down and to the right. And you should realize that in the full chart they would come back up like you saw in the schematic on the previous slide. But we don't really need that part. As a matter of fact, this y-axis doesn't go all the way down to 0.2. It only goes down to 0.3. But again, this is the most useful section of the chart. So the lines that are kind of sloping off to the right, those are lines of constant reduced temperature. Along the axis we have constant reduced pressure, and on the y-axis we have the compressibility factor. So this is the actual chart you would use for reading off compressibility factors. Notice that there are sort of dashed lines that slope up and to the right. Those are the lines of constant pseudo-reduced volume. You'll notice that it's labeled there on the lowest one, VR equals 0.70. Okay? Now you might notice something. If you pause the video and you looked for this chart and you found it in the metric appendices, you might have wondered, well, is it in the English appendices as well? And you went back and looked and you found it's not. Why would that be? Why would they not? I mean, does this not work in English units? Actually, it works fine. What you may not realize is everything on this chart is non-dimensional. So the reduced pressure is total pressure over critical pressure, non-dimensional. The reduced temperature is total temperature or absolute temperature over critical temperature, non-dimensional. The compressibility factor, even though it's PV over RT, PV has the same units as, or same dimension as RT, and so if you use consistent units, you end up with a compressibility factor that is non-dimensional. Same thing for pseudo-reduced volume. Okay? So this is a non-dimensional chart. Anytime you have a chart that is non-dimensional, or you start dealing with non-dimensional numbers, you typically really get at the nature of the behavior of the thing. Okay? I bought a house that was really ugly. If you've ever seen houses built back in the 70s, there's a lot of experimentation being done then. Seemed like they thought, let's break every rule, okay? Let's try something totally different. My house was a really odd house. It had an indoor-outdoor room. What that meant is the house was built around an outdoor room, and so you could walk into the house, walk through it to the outdoors. I guess they realized that was a bad idea after about a year because they put a roof over it, but they did a bad job with that. They ran 2x6s about 30 foot long. You could, if you know anything about building, you know that that's a fairly short beam for that span, and so you could actually get up there and jump on it. It was kind of like a trampoline. Kind of concerning. I've since changed the roof quite a lot, and so that is no longer an issue. But they were changing everything and trying things. So instead of having big, beautiful windows in the side of the wall, they put little bitty windows. And it was just the ugliest house I think you've ever seen. I don't know why I bought the thing. Actually, I do. It's because it had skylights in it, and I thought, oh, this is actually quite nice because there was so much light coming in. Well, it turned out those skylights leaked, and I had to replace those too. So don't be tricked by skylights if you ever buy a house, or you're looking for a house. You can install skylights yourself. Anyway, why is it that small windows, or windows that are very high in a large wall, look fairly ugly, right? Not very aesthetically appealing. Well, think about it as a couple of different percentages. Your eye automatically kind of measures the amount of area that the window takes up versus the area of the wall. And if that ratio is low, if you have a very small amount of area covered by the window versus a very large wall, it doesn't look very attractive. You could look at it this way. What about the width of the window? Well, if the width of the window is fairly narrow and the width of the wall is very high, it's an unattractive thing. Same way if the height is fairly small versus the height of the wall. Now, there's a good reason for not having huge windows in walls. It turns out that walls actually behave as shear walls. They prevent motion, or sort of a rocking motion of the studs. So there's a good reason to have what's called, I think they're called shear supports or shear walls. So you need some wall to help give some rigidity to it. Okay, you can't just fill up the whole wall with window, and that actually looks bad too. Have you ever seen a window that goes all the way to the edge of the wall? It looks very strange because intuitively you know that you need those walls there to help support the structure, so it looks unstable and unsafe. So of course back in the 70s they were experimenting with all this, and quite frankly a lot of it was ugly, and so I've changed this house where it looks much more classic, where it follows rules of percentages of area of the window versus area of the wall. And it, I was up on my roof one day, and the house was kind of disheveled because I had to tear into it so much. And my neighbor was walking by, and I was in the process of sort of putting things back together. It was actually beginning to look fairly decent, and he could see what I was doing, and he yelled, "Looking good!" We both lived down a gravel lane. I was up on the roof, and I thought, yeah, he's thinking, God, please don't stop at this point. Because, the house was changing so much, and yet if I'd walked away from it, it would have been an eyesore that was even worse than the ugly house because it would just fall apart. But anyway, he's a nice guy, and we're good friends, but I just thought of that at the moment he walked by. And now the house looks a lot better, and it actually sheds water a whole lot better, and is more attractive and so forth. But it's because that the house is following rules of percentages, or these non-dimensional measures now make a little more sense. So when you approach something by a non-dimensional number, you're really getting at the heart of the thing. And you'll probably do this, well, you'll definitely do this in your fluids classes when you deal with something called Reynolds number. Reynolds number is a non-dimensional number that separates turbulent flow from laminar flow. So hopefully you understand this in all of my meandering discussions. You should always be going through these with the slides open up as well. And when I work through an example problem for the compressibility factor, you should open up the slides because I've included some animations here. For example, I show you exactly where I'm getting numbers on the charts through the animation. So you should go to presenter mode, go through all these things and kind of see which lines I'm highlighting, so which values I'm reading off, okay, how I'm intersecting those curves in order to locate a unique point, and then reading from that point off on the y-axis to read the compressibility factor. This is always how you will approach compressibility factor problems in this class. So you should understand how I'm using the chart.